Let's now define what it means for a tree to be balanced. And for that, we need a definition of the heights of a tree. And let's now review our definition from earlier. Given a node, P, which doesn't have to be the absolute root of the tree, it can be anywhere in the tree. The height of the subtree rooted at P will be defined as follows, which we have seen already. So there are two cases over here. P over here can be either external or internal. So the base case would be when the P is actually external, in which case, by definition, the height of external node would just be 0. What about internal nodes? In that case, it will be the recursive case. It's going to be 1 plus the maximum of the height of the child nodes of P for all the nodes whose parent is actually P. That's the recursive case, right? So this definition here is something that we have implemented and also discussed before. You can definitely refer to the earlier part of the lecture if you want. And let's now introduce the so-called height balance property. In order for a binary search tree to be balanced, it must satisfy the height balance property. So what is that? Let's take a look. For every internal node n, we only worry about internal node. In fact, external nodes are automatically balanced. That's why we don't need to worry about them. But we're going to focus more on the internal nodes. And the heights of n's child nodes, which can be either left child or the right child, their heights must be different in their heights no more than 1. It can be 0, meaning that their heights are exactly the same, or their heights could be maybe one is h, the other one is h plus 1. However, it cannot be more than 1. If you got one child node with the height h, the other child node with height h plus 2, in that case the difference will be 2, which is not less than or equal to 1. So that'll be violating the property. So that's kind of the intuition you want to see right away when you see the definition. This will be one example binary search tree that's actually balanced, but I'm going to develop the heights property from scratch together with you. It's so important. It will also build a foundation for us to complete all the exercises we're going to do together this week. Let's take a look. Let's now focus on just this particular binary search tree. You can definitely verify yourself it's actually a binary search tree. Whether or not it's balanced, we have to see whether it satisfies the height balance property. To really check that, we have to figure out the heights for every node. So this is how I would do it, and you definitely want to make sure you work out a way for yourself to really fill out the height for every node in the tree. By definition, for external nodes, the height will just be 0. Remember our convention over here for drawing. We got internal nodes which will store some meaningful key values over here, whereas we also got external nodes which do not store any meaningful key value. That's our convention for drawing. Just don't forget. Will remain consistent for later drawing as well when we do the exercises for rotation. Let's start with this tree over here. By definition, all the external nodes are going to have the height 0. So I'm just going to put 0 over here, 0 over here, 0, 0, 0, 0, 0, 0, and 0. And let's now try to figure out the heights for the internal nodes. What about this one over here? By definition, it's going to be the maximum heights plus 1. The maximum height apparently is actually 0, right? And plus 1. So that should be equal to just 1. Right? So this is obvious, right? 1 will be exactly the maximum heights among the 2 plus 1. So once we figure out this one is actually 1, what about the heights for this one over here? This one over here, you can see the maximum heights for its child nodes, either left child or right child. Maximum will be 1. So that means the height should be 1 plus 1. That should be 2. Right, let's do the rest. And here, this one similarly, 0 and 0, the maximum plus 1. So this one should be just 1. Okay. And then, what about these two? These two will be very similar, so you can see the maximum heights for the child node will be 0 plus 1. That should be 1. Okay, and then this one over here, the maximum among 0 should be 0, and then plus 1, that should be 1. Hopefully, so far so good. What about the heights for this node over here? In that case, the maximum heights for the child nodes will be maximum of 1 and 1, which should be just 1. In that case, 1 plus 1 will be 2. Alright? And what about this height over here? The maximum amount these two child nodes will be 2 and 1. Maximum will be 2. Plus 1, 3. Okay? Finally, what about the heights for this root node over here? Maximum heights amount 2 and 3 should be 3. Plus 1 should be 4. That's how we figure out the heights for every node in the tree. Hopefully you can follow that, and you can definitely feel free to modify the shape of the tree and try to redo the exercise yourself, right? At least you should be able to do this example here, like how I did it. The first question over here, is the above tree a balanced BST? According to the definition, let's revisit that very quickly over here. For every internal nodes, heights of the nth child nodes differ less than or equal to 1. Let's check it for every internal nodes over here. Let's see over here. Let me just try to use purple over here. For this internal nodes over here. For this internal nodes here, you can see the heights for their children. The difference is simply just 0, right? Let me just try to, for this one over here, the two child nodes over here, the difference is actually 0. And for this internal nodes over here, the two child nodes are over here. In that case, the difference is 0 and 0 is also 0. And let's now move on. What about for this internal nodes over here? In that case, the two child nodes are over here, and the difference is actually 0, because you can see 1 and 1. Right? Let's do some similar exercise. And what about this internal nodes? The child nodes 0 and 0 for their heights, so the difference is actually 0. And for this internal node over here, the child nodes will be 0 and 0. So the difference is also 0. And what about this node over here? The child node is actually 0 and also 1 over here. In that case, 0 and 1, the difference is actually 1. Right? So that's still okay, because as long as it's less than or equal to 1, that'll be fine. And then what about this internal nodes over here? In that case, we got these two child nodes and their heights 2 and 1. The difference is actually 1, which is good. What about finally this internal node over here? The child nodes over here, the difference is 3 and 2. The difference is actually 1. So we have checked for every internal nodes in the tree. And we have seen that for every internal node in the tree, their child nodes, for example, these two child nodes for this, or these two child nodes for this, and etc. The difference is no more than 1. We got 1, we got 0. We don't have anything strictly larger than 1. So that's why it is balanced. So the answer is yes, as we have worked out the details. Right, so that'll be the first part I want to go over with you. Given a binary search tree, you want to make sure, number one, how you can fill out the heights for every node, including internal and external. And number two, how you can check whether or not the tree is itself balanced by checking for every internal nodes. Their child nodes heights must be differing less than or equal to 1, according to the definition. Right, so what we will do now is we want to actually talk about another two questions. So this one is already checked. Okay, what if we try to make some like an insertion? We want to change the contents of the tree. In that case, can it actually violate the high balance property? It may or it may not. It depends. Let's now take a look at two examples over here. Okay, the first one, let's see what we want to do. Let's say we want to insert 55 into the tree. In order to insert 55 into the tree, we start with 44, and then 55 is larger than that, so we should really go this way over here. And then 55 is less than 56, we go this way. 55 is larger than 48, so we go this way. And then it's larger than 51, so we go this way. So this will be the external node that will be returned from the searching process. So according to what we learned before, we're actually going to turn this into an internal node over here. So that right there is going to be 55 over here. And then that one there also has two external nodes. Like that. That's what we have. And now we're actually going to update the heights of the tree. Right? So that's why I kind of cover what we used to have before, because they will be changed anyway. But we can actually see exactly how they will be changed. You can think about these heights are before the insertion, but after the insertion, we're going to do something maybe a little bit different. We're going to update them. Okay, that's what we'll do. Let me just delete it. Okay, and let's now try to do that. Let me use maybe blue again. Okay. External nodes, let's fill out their heights first. They're easy. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Apparently, you can see for this part of the subtree is unaffected, right? You can see 0, 0 plus 1, 0, 0, maximum 0 plus 1, right? So this part here doesn't really change. This one may have to change because it might be affected by the insertion, which is going to somehow impact this half of the tree. We'll see. Let's now try to see. Let's go bottom up. What will be the height for this node over here? 55. 0, 0. So that should be 1 over here. What about 51 over here? You can see this one will already change. 51, the child node's height will be 0 and 1. Maximum will be 1 plus 1. So this will become 2 over here, right? And also 0 and 2. 0 and 2. Maximum is 2 plus 1. So this means this was going to become 3. 0, 0 over here, and plus 1. That'd be 1. So this part remained the same. And what about this part over here? 3 and 1, maximum is 3 plus 1, that will be 4. And then 2 and 4 over here, maximum will be 4. So 4 plus 1 is going to be 5. That will be the updated heights for every node to begin with, before we can decide whether after the insertion the tree will become unbalanced. Let's now see which part will be unbalanced. Let's find out all the nodes that become unbalanced. Okay. Apparently, you can see this part over here. This part over here is actually okay, right? This part here, you can apparently they are not really affected. This part here, let me not even put a difference. They're just the same as before. Okay. And this one here, you can see the difference is also 0. And let's now see this. This part here, this node itself, this node over here is balanced because 0 and 0, the difference is 0. So this node is actually okay. Okay. And what about this node over here, 51? That node is also seen to be okay because if you can see the balance over here, the height 0 and 1, so the difference is also 0. However, if you look at the 48 over here, that one does not seem to be balanced because if you look at the two child nodes over here, the external node and the 51, you can see the height will be 0 and 2. So the difference is actually 2. Let me just try to highlight it. You can see 48 over here. Let me just try to make it more explicit for you. You can think about 48 is no longer balanced, right? No, because the difference is actually 2. That's the first one. Is there any other one? Let's take a look. What about the 77 over here? That one seems to be still balanced because if you see 0 and 0, the two child nodes, the difference is actually 0. Okay, and then we also got what about the node over here, 56? That one does not seem to be balanced because if you look at that, these two nodes over here, the child nodes, the height will be 3 and 1. The difference is actually 2. The difference is actually 2. So that means this 56 is also not balanced. Okay, and there's a reason for me to circle that. I'll give that. I'll tell you in just a moment. And then finally, how about the nodes over here at the root? If you look at that, it doesn't seem to be balanced because the two child nodes over here, we got a height 2 and also 4. So the difference is actually 2, which is larger than 1. So this one also is not balanced. Okay. So it turns out after the insertion of 55, we actually resulted in 1, 2, and 3. 3 nodes that become unbalanced. And one thing to note, can you see some very common characteristic between these 3 nodes? You can feel free to pause the video if you want to think about it in terms of where they are in the tree. It turns out when you try to do an insertion, if it can cause any ill balance to the original tree, the nodes that become unbalanced must be along the way to the ancestor path of this particular node that's being inserted. For example, you can see 55 over here. What would be the ancestor path? It will be 55. Let me just write it down explicitly. So the ancestor path of the 55 that's being inserted, right? This will be a very important observation for you. So I'm still talking about question number 2 over here. So the ancestor path will be 55, 51, 48, 56, and 44, right? That's all the way up to the root. It would be including itself. So it will be 55, followed by 51, followed by 48, followed by 56, and then 44. And you can see that this is where things become unbalanced. Starting from 43 over here, so these are the three notes that become unbalanced. Unbalanced. After insertion. So this will give us some insight. Whenever you try to make an insertion somewhere in the tree, and if you want to fix about the, you want to restore the balance after the insertion. For example, you want to fix the balance for this node here, and this node here. You want to really fix the node only along the ancestor path. All other nodes outside the ancestor path for the node that's being inserted, they simply got they don't really get inferenced, so you don't need to fix them. So ancestor path is really somewhere that we're going to touch later for the fix. Okay, the ancestor path over here, this is where the fix will need to be, and which we're going to talk about when we get to rotation. So the ancestor path is really where rotations need to take place. And for now, you don't need to know about what rotation is. It will be covered a little bit later. Okay. What about the third question over here? Let's say we want to insert another value over here. Let's say we still got this tree to start with, and we want to insert 63. Let's say, how can we do that? Let's take a look. And for this one here, let's still do the exercise together with you quickly. But I think it will be very important for you to grab a piece of paper and also do the exercise yourself. Right? For this one, let me use green. I can tell you the answer should be, it does not really cause any unbalanced node. So that means insertion does not always produce unbalanced tree. It may or it may not. So you gotta check. Right, so we're gonna put the node balance over here. We got let's now insert. How do we insert 63? So 63, we're gonna start with the root. So you should go to the right of 44, and go to the right of 56, and go to the left of 677. So this will be where it should come. So what's going to happen is we're going to convert this into an internal node over here, and that one there is 63. Okay, 63, and then we got two external nodes over here. And let's now fill out the balance. I mean the heights. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, all 0 for external nodes. And let's now reval the heights over here. The heights that used to be calculated before the insertion, let's see if any one of them need to be updated. If none of them need to be updated, that means we haven't really caused any unbalanced tree. We'll see. Let's see. Is this node height need to be updated? No. 0, 0, and then 1. Very good. And how about this one here? You can see 0, 1, maximum is 1 plus 1, that'll be 2. Awesome. How about this one over here? What will be its heights? 0, 0 over here, that should be 1. Let me put it down first. So this one over here, the height should be actually 1. And what about the heights for this internal 77 over here? It need to be updated. So maximum for the two child nodes will be 1 and 0. So this should be updated to actually 2, which is okay, because if you compare these two child nodes over here, it wouldn't cause this node to be unbalanced, because 2 and 2, the difference is actually 0, so that's fine. And what about this node over here? Does it need to be updated over here? It does not need to be, because maximum of 2 and 2 is still 2. In that case, it will be 3. And for this part over here, it's unchanged. It's not really influenced by the node that's being inserted over here. Finally, would this node be should this node be changed for its heights? 2 and 3, the maximum will be 3 plus 1, that'll be 4. So it looks like the balance is actually unchanged. I can let you do that complete exercise yourself, but let me just focus more on the ancestor path for the node that's being inserted. You can see this part over here. This will be the node that's being inserted over here. The difference for its child node's height will be simply 0, right? What about this node over here, its parents? in that case, if you try to look at these two, right, one will be 63, the other one, the external nodes, the difference is 1, which is still acceptable, right? What about the grandparents over here? So the two nodes heights will be 2 and also 2. So the difference is actually 0. So we are fine. And what about here? The difference remain to be just 1. 2 and 3. The difference is actually 1. Right? So this insertion does not really cause the resulting binary search tree to be yield balanced. So the conclusion is, whenever you want to do insertion, whether or not some rotation or some restoring of the balance need to be done depends on whether the resulting tree is still balanced. If it is not, then of course you got to do something about it. Right, so the answer will be this one here. It is still a balanced binary search tree, but for the previous one, it would be no. Right, so you want to study these examples very carefully about annotating the heights and also determining for each internal node whether or not it's actually balanced, depending on the heights of their child nodes difference.